A diatomic ideal gas starts at a pressure of 1 times 10 to the 5 Pascal and a volume of 8 milliliters, and is then compressed adiabatically to half a milliliter. What is the final pressure of the gas, and how much work was done to compress it? And what did this work ultimately accomplish? Now, the first set of questions there, I think, are things that could be calculated, and the second question is more of an interpretive kind of question. Uh, what formula should I use? Well, I really have two formulas, right? I've got this one here that relates the final pressure and volume to the initial pressure and volume. And then I have in my table the work formula, where if I have the initial pressure and volume and the final pressure and volume, and if I know the value of gamma, I can calculate that amount of work. And in this case, I mean, we mentioned in the key concept slide that for a diatomic gas, gamma is equal to 7 over 5, but 7 over 5 is equal to 1.4 and is given to us here in this question in case we had forgotten that value. I'd like to move this formula over a little bit though, give myself a little space. So I'm going to put it over here to the side, but I think that's the one that I'd like to maybe use first. And to see why that might be, I wanted to use this corner to write down some of the quantities that I've been given here. And I think I can assign to initial pressure the 1 times 10 to the 5, and maybe I'll write that here as 1.0 for the sake of brevity. I'm not writing all the significant figures. I can always look back at those later to decide how I want to round. And in this class, I've kind of said that's a little bit optional anyways. I can establish that there is an initial volume of the 8 milliliter. Oops, let me make that look a little bit better. And maybe I'd like to convert that. It turns out there's 10 to the 6 milliliters in a meter cubed. And the way you can know that is there's 1,000 milliliters in a liter, and there's 1,000 liters in a meter cubed, and 1,000 times 1,000 is like 10 to the 3 times 10 to the 3, total of 10 to the 6 there. So that means this is actually equal to 8 times 10 to the minus 6 meters cubed. And I think it'll be handy later to have that in terms of a base unit, so that's why I'm doing that. The final volume is given as that half a milliliter at 3 significant figures, so we can note I think everything here is 3 significant figures, so that gives us an idea of what the expectation might be for rounding final answers. But this could as well be written, if I want to, I guess I could write it as 0.5 times 10 to the minus 6. If you ever had a teacher tell you that's not proper scientific notation, well, don't tell them I did this, okay? I should have maybe written as 5, what would that be, like 5 times 10 to the minus 7, actually, in proper scientific notation, but this will be easy enough for me to enter into the calculator, so that's okay as well. And since I have these 3 quantities, and the first part of the first question there is what is the final pressure equal to, it seems clear that this formula will do the job for that because it has those same 4 quantities. And I didn't write over here that gamma is equal to 1.4, but I do know that from the problem statement, so we'll be able to use that. So I can isolate using this formula here. I can isolate that final pressure by dividing by the V raised to the power gamma on both sides. So that'll be equal to P naught times, I'm going to write it as V naught to the gamma divided by V to the gamma. That might be convenient because I could just rewrite that. I like to do it this way. You don't necessarily have to do it exactly this way, but I'm going to distribute that exponent. I like doing it that way because it's going to make the units, I think, a little bit more transparent. And so with this expression, I can plug in all of these values. So I can put in the, I'm just going to put in 10 to the 5 here for the sake of brevity, Pascal, multiplied by, and I'll put in the, for this one, I'm actually going to put in the 8 milliliter divided by the 0.5 milliliter. And since I've written it this way, now maybe it's revealed why I did that, because it's very clear that with that exponent kind of distributed out, that these units cancel, which is expected, I think. And then this is something I can put into my calculator to see what result I get. And I get 400 and, hang on. Yeah, no, 4 million, excuse me, 4,850,293, like 0.013. Maybe I could rewrite that as 4.85, and then let me make sure I count. Yeah, I said million, right? That should be 10 to the 6. I always want to make sure I get that correct, though, because this human being has made many mistakes with that in the past. So I've learned to be careful when looking at powers of 10 and not to accidentally make a mistake. It's especially important when you're doing your taxes. You don't want to pay too much. So, okay, that's the result for the first part of the question there. It's also asking for the how much work part. And so for that, I will use this formula here. In other words, I'm going to do P naught V naught minus P times V divided by gamma minus 1. Well, I think my gammas are getting messier every time I write them now. So that'll be about like this one. I think I'm going to want to make sure to be careful about units. So I'm going to write 10 to the 5 Pascal for the initial pressure there, but then I'm going to multiply that by 8 times 10 to the minus 6 meter cubed, because I think a Pascal times a meter cubed is going to be a joule, which is what I'm expecting here. I'm going to have to subtract from that, though. Bear with me here. This is a long thing to talk about that. But we're going to have to subtract the, maybe I'll just write right here the 4.85 times 10 to the 6. In my calculator, I was able to take the unrounded version of this, but I don't think I have enough space to write all that. So that'll be that multiplied by, whether I have enough space for the other thing, I'm just going to put down here, times the 0.5 times 10 to the minus 6 meters cubed. So pardon the way my expression is looking there. Looks far nicer in the calculator, I could say that much. And then gamma minus 1 is really 1.4 minus 1. So I could already go ahead and in my head subtract those two numbers and say 0.4 represents gamma minus 1. And then I put all of that into my calculator, and my calculator actually gives a negative value for this, minus 4.0, maybe 6 is good enough, right? Since we said 3 significant digits is what we're looking for here, and that should be in joules. But now maybe time for a little bit of interpretation, because this formula was the work done by the system, and this question is for how much work was done to compress it. So I'm thinking that that's how much work was done to this system. In other words, a person did something, and we actually have a setup that we do a lab on sometimes. In our lab, that is, we have a setup where we have this like cylinder, and if you compress it really, really fast, you can actually light little bits of paper that are in it on fire just because of how high the air temperature gets to be in the cylinder. A dramatic demonstration of this type of a compression that we can actually do in our lab, and that might actually lend itself to answering the last question there. But since we're being asked for how much work, the person doing the compression would be doing a positive work. So even though I got a negative number here, that's the work done by the gas, but a negative work done by the gas really means positive work is being done to it. So I should revise my answer to a positive 4.06 joules based on this interpretation. And then based on the description I just stated for the demonstration apparatus that we sometimes do a lab with, what did this work really do? Well, that's something I think we can answer based on the first law of thermodynamics, as well as what I just described. I mean, I said we light these little pieces of paper on fire, and so you could say, well, this work accomplished getting some air really, really hot, right? But from a first law of thermodynamics perspective, there was negative work done by the system in an adiabatic process. So Q is equal to 0, right? So if you think about, let me write it down. Q is equal to change in thermal energy plus work. And we just got a negative result for this. And I mean, this doesn't look like a lot, but it turns out air being not very dense, and this being a relatively small volume of it, it turns out this amount of energy loss, energy gain, I meant to say, because it's really a negative value for this, so that would have to be counterbalanced by a gain of delta E sub t to set Q equal to 0. That implies a huge temperature increase. So really what the work accomplished is that the air gets hot, in the sense of, again, a high temperature is how I'd like to quantify that. So another calculation that we didn't do here is to possibly ask the question, well, how hot would the air get based on some starting temperature, and that might be able to explain why it's possible to light little tiny bits of paper on fire with a demonstration of this. Let's check what the slide says. It says 4.85 times 10 to the 6 pascals, so that looks good. And then it says 4.06 joules, and we caught that sign issue in our interpretation. And then it points out that assuming this was a gas sample that started at 20 degrees Celsius, so I said earlier that's what we'd need, right, if we want to actually calculate a final temperature, it winds up at a whopping 615 degrees Celsius, which, although I don't necessarily know what the exact ignition temperature of little bits of paper are, I think that number convinces me pretty well what is going on with a demonstration like that.